Hi everyone, let's solve today's daily challenge that is as far from land as possible. So in this question we are given an n-cross-n grid which contains only values 0 and 1 where 0 represents water and 1 represents land. And we want to find a water cell such that its distance to the nearest land cell is maximized and we have to return that distance. If there is no land or water cell that exists in the grid, then we have to return -1. And the distance used in this problem is the Manhattan distance. Okay, so let's look at the problem. So I will not be taking the test cases given in the question because they are a bit confusing. So let me take a different test case, that is 1 0 0 1. And so let's consider we are given this grid, right? So first thing is that 1 represent that at this particular index we have land, and 0 represents that wherever 0 is we have water, right? So let me, okay, so for a better explanation, let me write these with different pens. So let's for water take this pen. Okay, now it is more clear. So wherever 1 is, that is land, and wherever 0 is, that is water. Now we want to calculate the Manhattan distance. Let's also look at what Manhattan distance is. Manhattan distance is nothing but, let's say this is located at 1 comma 1. So if this is located at 1 comma 1, if for this 0 we see, is it located? It is located at 2 comma 4, right? So you just simply, let's say this is x1 comma y1, and it is located at x2 comma y2, then the Manhattan distance between them is nothing but x2 minus x1 plus y2 minus y1. Okay, and this is the mod, right? We just take the mod of these values and that is the distance. So now Manhattan distance is also clear to us. So whenever we are referring to distance, we mean the Manhattan distance. So now let's see the question. So in this question, what we want to do is we want to return this maximum distance that we can get from a particular water cell to the nearest land cell, right? So first we have to consider the distance, maximum distance from water cell to the nearest land cell. Okay, in this question, if you see in this test case, this particular 0 we can see is very far from this one and from this one as well as from this one, right? But the nearest one is this from this 0. So we have to calculate the distance from this one to this 0, and that is the answer, right? So from here, if we go from 1 to this one, this is 1 distance, this is 2 distance, and this is 3 distance. So the answer to this test case would be 3. Why? Because if you take, let's say, if you take this cell, right? If you take this particular water cell, then you can see that its distance, like it is also very far from this one or this particular one, but it is very near to this one. And from, if you go from this one to this 0, then you will be getting a distance of 2, which is not the maximum, right? For this particular location, for this particular water cell, we can see that 3 is the maximum distance that we have, right? So that is what we have to see. We have to maximize the distance from the nearest water cell, oh sorry, from the nearest land cell. That is what we have to do, right? So, and also if you consider any other cell in this question, it will not, you will not get an answer more than 3. Why? Because if you even consider this is very near to this one. If you consider this particular cell, it is also again very near to this one. If you consider any of these cells here, they are again very close to this one or either this one, right? But this particular cell is the farthest from all of these cells, and we have to consider this cell, that is the nearest land cell, and from this cell we have to calculate the distance, right? So let's see. So one thing that you might be noticing here is that this is a graph problem, right? Why is this a graph problem? Because we are considering we are considering some paths, right? And they are not like in a linear fashion or anything, right? From this one we are considering some paths, right? Will be traversing in some of these paths, right? Or any of these paths, correct? So one thing is that this is a graph problem. So how can we find this particular cell or the distance for this particular cell, right? So one approach that might come to you is BFS, right? But the problem with just BFS will be that how will you consider these all of the ones at once, right? So we want to do that. So to consider all of the ones at once, we use something called multi-source BFS. So in normal BFS, what do we have is we have we start from one particular position, right, in the graph, and then we take the adjacent of this graph, and then we remove this particular from the queue, and then we keep moving for, then we consider for these, right, the adjacent of these. So any point at any point in the queue, we have at max two levels, right? Only two levels in normal BFS. But what multi-source BFS says is that whatever nodes that you want to take, right? Whatever nodes that you want, let me erase these things. Whatever nodes you want, you just take them and say that they are at a, like they are at initial points, right? Because in this question we want these to be our initial points, right? All of these, but at once, right? So we say that 1 and 1 and 1, we say that they are at 0th level, okay? And then we move forward. For this particular one, we will be taking its adjacent element. For this particular one, we will be taking its adjacent elements, and so on. And then we keep moving forward. So let's say if we consider this, right? So if we consider a normal BFS from this one, so at what level will this 0 be at? So if you go from this 1, 2 and 3, so it will be at 3 level for this particular one. But for this particular one, if you see, it will be at 2nd level, right? But it will be present inside of this, and it will be present at the 2nd level, right? So that is what a multi-source BFS is, and that is what we'll be using. So it is like a normal BFS, but it's just that we take all the initial nodes that we want, and we consider them at the 0th level, and then move forward with the same logic as we use in BFS, right? That is queue, and then you take all the nodes and then consider for them, right? So let's see. So let's consider the queue. So in the queue first, what we'll be having, this node and this node and this node. So inside of the queue, we'll be storing the position of this node. So let's say it is 1 comma 1. The position of this node, that is 4 comma 1. The position of this node, that is it will be 3 comma, sorry, it will be 2 comma 3, right? So we will be taking these positions. Then what we'll do is we will keep doing our BFS, right? So first we will take this node, and then we will take the adjacent nodes of it, okay? And we will also take a maxi variable, right? Inside of this we will be counting the number of BFS that we had to do, right, to reach this particular cell, right? So let's see how we'll be getting an answer. So from here we will do BFS, and we will store these inside of the queue. Okay, so right now inside of the queue, okay, let me make the queue here. Let me erase this and make the queue. Okay, inside of the queue right now we have this 1 comma 1. This was 2 comma 3, and this was 4 comma 1. So right now we have these inside of the queue. Now we will take the adjacent elements of these, right? So if we take the adjacent elements of these, this will be 2 comma 1, this will be 1 comma 2, and we will remove this from the queue. Then we'll move forward and we will consider this. So for 2 comma 3, we will take the adjacent ones. Okay, so this is the very first iteration, right? So we'll consider these. So at one particular point, we have to consider four possibilities, right? Um, One for the upper one, then towards the right, towards the left, and towards the towards downwards. We have to check whether there exists a node or not, and then we have to consider in BFS. For this, we only had two nodes, right? Because here we don't have anything, and here we don't have anything. But at particular index, at a particular index, we'll be having four possibilities, right? We can have an adjacent element here or here or here or here. So we'll see it in code better, right? So we'll be considering these four possibilities, and then from there we'll be taking the adjacent ones, right? So for this we'll be taking four values that are these. Okay, we'll take them inside of the queue, right? Okay, let me take these inside of the queue. So it was at 2 comma 3, so this particular is 1 comma 3, right? And this one is 1 comma 3. Also, whatever node that we visit, we will mark it as 2, right? Whichever are visited, we will mark them as 2, right? This is also visited, so we'll mark it as 2. So first let me write all these values here. So first is 1 comma 3. It will be 4 comma sorry, again so it is 1 comma 3, and it will be 2 comma 4. This one will be 3 comma 3, and the upper one will be 2 comma 2, right? So these are the values. Okay, now we will remove this from the queue, then we will move forward towards this one, this particular index, and then we'll do BFS and we will get these two, right? So again, when we are done visiting, we will mark them as 2, right? So now what we'll have inside of the queue, we will be having this particular index and this particular index. So this is 3 comma 1, and this one is 4 comma 2, right? Then we will remove it from the queue. Now we have 2 comma 1 inside of this queue. So 2 comma 1. So it's this one, right? This particular. So if you see its adjacent elements, it is this and this. They are already present inside of the queue. So we'll not be getting anything inside of the queue for this particular index, right? So this was the very first iteration, right? This was the very first level, and we have completed the iteration for that. At the end, we will increment max of I. Then we will move forward to the rest of the levels, right? So for 2 comma 1, we will not be inserting anything, and then we'll remove it. This is the second iteration. Then we will move forward to 1 comma 2. 1 comma 2 is this particular index, and again if you see, all the indexes that are adjacent to this are already in the queue, are already visited, right? So we will remove this from the queue and then move towards next index, that is 1 comma 3. So 1 comma 3 is where 1 comma 3 is this particular value. So from here we can go here, right? So we will insert it inside of the queue, that is 4 comma 1, right? And the rest are already inside of the queue. So now this is also visited. Now we'll move forward. We will remove this 1 comma 3 from the queue. So we've started inserting here, right? So up to here we have the second level. Okay, so then we will consider 2 comma 4. 2 comma 4 is this particular value, and this is not yet visited, so we will visit this. So when we will be visiting it, we will be getting inside of the queue 3 comma 4, right? It will be inside of the queue, and this is also visited. Let's mark it as 2. Then we'll move forward and we will remove it from the queue. Then we will consider 3 comma 3. So 3 comma 3 is this one, this particular value. So if we consider its adjacent ones, so we'll be having these and these. Okay, so when we'll be having these, we will insert them inside of the queue. Okay, then after we are done for this level, we will be traversing for this level. Okay, so if you see that the number of levels inside of this BFS, inside of this multi-source BFS, is actually our answer, and that will be stored inside of this max I. Right, so I think you have now got the gist of what we'll be doing. So let's quickly implement it. Okay, so let's quickly implement it. So what first of all, what we'll be doing is, let's take the sizes, right, of this grid, right? So this is for the row. Then for the column, we'll get a size, that is grid of 0 dot size. Now we'll make our queue, and as we saw inside of the queue, what we'll be storing is that particular index, right? That particular point where it is located. So it will have first x and y. So for that we'll be creating a pair. Okay, and inside of this we will be storing. Now let's traverse inside of this grid. So first of all, what we'll be having inside of this queue, right? Where are we starting? We are starting at all the places where we have one, that is wherever we have land. From there we are doing the BFS, right? So we'll first take all these inside of our grid, right? So let's traverse. Let I is equal to 0, I less than r and I plus plus. And in the second loop, it will be int j is equal to 0, j less than c, and j plus plus. Now we will check if grid of I and j is equal 1, then what we'll be having? Then we will be putting it inside of the queue, right? So we'll say queue dot push this particular value, that is I comma j, inside of the queue. And also we have to mark it as visited. So for marking it as visited, what we were doing, we were just simply putting 2 in there. So to put in 2 in there, we'll simply say grid I comma j is equal to 2, that it is visited. Now first we have taken the first level inside of the queue. After this, also we will have a base case where edge case, sorry, we will be having an edge case, that is when we will be having all ones or all zeros inside of this matrix. Then we have to return -1. Why? Because in that case we cannot find any distance between land and water, right? Because we will be just having water or just land inside of the grid. So how we'll check that? If this queue, right, if this queue contains all the elements, that is if the size of the queue, right, if we have only land, then the size of the queue will be equal to the number of cells, right? So the number of cells will be r into c. So if q dot size is equal to r into c, so that is the case for land. And for water, what will be the case? If there is nothing inside of the queue, that means we did not get any value where there was land. So if q is empty, or q dot empty, right? So this, if q is empty, this will return true. So in both of the cases, we have to return -1, because in those cases we'll not find anything. Now we'll be writing our main logic. So first let's initialize our max I variable, which will initially contain 0. So we'll say if q is not empty, right, then we will be traversing inside of it. So let's take for the very first level, let's take the size of the queue that we have, that is q dot size, and we'll be traversing inside of this particular level now. So let's take inside of this particular node, inside of a variable, let's call it node only, and we'll take the first value and we'll remove it from the queue also. Now as I said, what are the possibilities? We have to check, like as we saw here, there are 4 possibilities, right, in which we can have any adjacent element. So an adjacent element will be present at this position. Okay, let me take a different pen. So we have 4 possibilities, right? So let me draw the matrix here only. If we have this, let's say we have this, right? If we have this kind of a matrix, so for one particular index, we have four possibilities, that is upwards, downwards, left, and right. Here we can find an adjacent element, right? So for that, we'll be having a for loop and we'll be checking all these four possibilities, right? So we'll iterate from for int I is equal to 0 and I less than 4, I plus plus, and we'll be checking for these possibilities. Okay, so how we'll be checking these possibilities, right? So if you see to get this particular upwards element, what we have to do, we have to simply decrement in x direction we are doing nothing, so it will be adding 0 to the x direction that we already have and minus 1 to the y direction to get the upwards element. If you want the downwards element, then it will be 0 comma 1, or if you want to get this one element, then we'll be adding nothing in the y direction but in the x direction, that is subtracting 1 and this. So we will be doing this, and for this particular direction what we'll be doing, we will be adding 1, and in 0 in y we'll be doing nothing, so we'll just add 0 to it. So let me create vectors for these here. So we'll just say const dx vector int dx. It will be storing values as 0, 0 and 1, minus 1 and 1. Okay, so its corresponding values in, we'll take another vector, that is, we'll call it dy, and for the corresponding values it will have minus 1 or 1 and 0 and 0. So if we just take the ith element of these vectors, we can simply add them as dxi and dyi right inside of these. So I'll just take two more variables, let's call them next of I. So what will it contain? It will contain whatever we have at this particular node, right? So how will we get it? We will say node, right? We'll be having this node is what? It is a pair, right? So node dot first value plus we will say dx of I, right? And int of next y we will calculate, that is next j, we'll just say, and node dot second plus dy of I, it will be, right? So from here we will be taking all the possibilities. Now we will check if this particular possibility that we have considered, if it is a water cell. So how will we check if it is a water cell? So we will just see if it has 0, right? So we'll just simply check grid of this. Okay, first of all, these should be inbound, right? How will we know that these are inbound? First of all, they should not be negative, right? If next I is greater than equal to 0 and next of j is also greater than equal to 0 and also and this is one condition, and the other condition is that it should be in less than r and c, right? Let's say these both are positive but they're greater than r and c, then also we'll be going out of the boundary, right? Out of bounds. So we have to check that next of I should be less than r and next of j, it should be less than c. So we have to check for this condition also. So if this particular index exists, then we have to check if it is a water cell or not. If it is a water cell, that is grid of next of I and next of I comma next of j, if it is 0, then what we'll do is we will push it inside of the queue. We will say q dot push this grid of next of I comma, okay, sorry, it is not comma, it will be next of I next of j, next of I, next of j, right? next of j, we will just push it inside of the queue, and again we will mark it as 2, right? That we have visited it, that it's visited. So now we'll be doing a BFS for this, for all these possibilities. That is how we'll be doing it. And then after this loop, simply we have to increment this max of I. And by the end of all the levels, right, after we are done with this, we will simply return max of I, right? But there is also one thing, that at the end of the very last level, the max of I will be incremented one more time, right? So we have to subtract 1 from here, and this is how we'll be getting the answer. So what we are doing, so we simply are doing multi-source BFS. In multi-source BFS, we say that we take multiple sources, right? So unlike the normal BFS, we take multiple sources, and from those sources we do a normal BFS that we usually do, right? We do a BFS like this, but initially it has multiple sources. So we have created those multiple sources here, and then we have this base case that if there is only water or land, then we have to return -1. Otherwise, we'll be traversing inside of this while loop, and we know that all the levels, right? The number of levels is actually the answer. Okay, so let's quickly run it and let's see if it is working or not. Okay, it is const, right? Where do we need line 38? At the end of declaration list. Okay, so this is for the while loop, this is for this while loop, this is for this for, and with this if conditions, and this is also for these if conditions. Where are we missing this then? Then also we have this if condition. For this, do we have anything? Okay, we have one extra. Okay, this is for this. But we already have this, right? Okay, we don't have this here. Okay, sorry, we will not be pushing the grid here. We will be pushing only the next I and next chain side of it, because it's a pair, right? Okay. Okay, so it's accepted. So this is how you have to solve this question. So the time complexity is O of n square, right? First, and the space complexity is O of n. Why? Because we are using a O of n square only, or not O of n, because we'll be using this queue, and at once we can have R into C cells inside of this queue. So both time complexity and space complexity are of O of n square.